last thing I'll say before we dig into the tutorial, common pattern that's come up in a lot of hutches is that people will run this parallel Python on the big data. And then you save your little data in an HDF5 file. And you get that, say, right after the run ends, within a minute, something like that. And you move it to your laptop, and then you use whatever tool you want to analyze it. MATLAB, Igor, IDL. HDF5 is readable by now. So now we'll start digging into the tutorial, where we're going to go through a set of examples. So if you've looked at it before, you might want to look at it again. It's much more Python-centric now. We've tried to eliminate patterns that we think are no longer used, to clean it up. The main thing we're going to do is be going over these building block examples section in the documentation. You don't need to open up your web browser. It's not necessary. I'll show you. So now the first thing we'll do is get you would have to reshape it into a two-dimensional image to plot it, just like we do with the cheetah unassembled image. And so in Python, that would be, roughly speaking, a one-line command. You would do numpy.reshape, and you would give it the three-dimensional array, and you would specify how you wanted it reshaped into two dimensions, typically by contracting two of the dimensions into one, and then plotting that as a 2D. So now we run this script. Let's just show you how to. So Python space and 03, and then hit tab. And then your CSPad image shows up. In this case, the assembled with the applied geometry. You can see all the little gaps between the panels, and that's the applied geometry. One thing you'll see in the later demos, we talked about this being a calibrated image, but we'll show you the tools we have for managing calibrations, which are important. Add pixel mask, and with a few lines of Python, you can have more control over precisely what happens. This is kind of the simplest user interface for people who want to accept what we've done, but we try to give you the ability to do your own thing as well. So what you're seeing here is effectively the old interface, which I believe we have a good plan for making it go away because it's more complicated. But I think it's important to show you because it's still there. And the other thing, in the simpler interface, is kind of giving you a subset of the information. With this interface, you can really go back and get everything about the detector. So it is important to know about this interface, but hopefully most users can remain blissfully ignorant. As always, please continue to raise your hand if you want help.
But then there are the special codes that you really care about, honestly. You really care about 162, you care about what your hutch uses. So XPP, for example, uses a set of 90s. And then we can set it up to mean whatever we want to. We have kind of a convention, but you kind of do need to talk to an instrument scientist. So, at this moment, there's no standard way to basically put this somewhere in your data.
Because the experiments change all the time. Yeah. The principle of meaning what. Okay, the next example, number 6. Cat space. So once you're in array land, then you can do all sorts of cool things very easily with just single lines. And you can have control over what's happening. This is how you jump to an event, which I think is very important. It turns out the basic idea is, it's not obvious, but it's related to how we parallelize. So this idea is critical. It's also critical for things like hit finding and crystallography. We're going to try and push to see if we can get this out of this company called MRF in Finland. We only had 17 bits to identify the event effectively, and it rolls over every 20 minutes. And since LCLS is going to last longer than 20 minutes, that's not so useful. For LCLS 2, the timing system is being redesigned, and this will be one 64-bit number that will uniquely identify every LCLS shot. So that problem with the timing system propagates up to our code, and it makes our code look ugly. Because this idea is key. And I think I spent a lot of my life working on big parallel systems, both in high energy physics. I've worked on GPUs, parallelize things in FPGAs, these programmable data arrays, custom electronics and stuff like that. And in my judgment, this MPI thing, at least that I know of, is the best option that we have. It's supported at computer centers around the world. So when you move labs, you can reuse the same tool if you go do an experiment somewhere else. Any serious computer center. Over at NERSC, 90+% of their jobs, it's all MPI. That's how people parallelize. Because the batch system figures out which cores are free, and it can distribute your job for you. And you have some control over that. And then you get 10 pipes to the data, so that different cores can be parallelizing your jobs. So this MPI thing, I haven't heard of anything better for us. People talk about replacements, but this has been a standard now for 20 years. And I guess it was invented in the early 90s. But then there are tools where you can draw on the associated image. So here and this is an important idea, so I'm going to take a minute to explain it. The correct pattern is you always want to do your physics, ideally, with the unassembled images. Because an assembled image has got fake pixels in it, for example. You put up all these panels and you've got fake pixels in between. And then that kind of just makes your analysis ugly. I'll show you how to do it a little later on to determine which pixels are fake. But in general, if you can work with the unassembled images with no fake pixels, your analysis will typically be cleaner. You have less exceptions to worry about when you're worrying about fake pixels. So that's the pattern we try and use. Work with the unassembled images, then at the end when you're done, you apply the geometry and turn it into an assembled image. When I used this in No Machine earlier on, sometimes it came up very big, and so you couldn't see the bottom of it. If you end up having a problem like that, you can't see the bottom of the GUI, then raise your hand and one of our people will try and help you. But you can just follow along on the screen too if you prefer. We use this we're going to demonstrate three things with this. Three of the tabs. One is dark runs. This is routine. You do this all the time in LCLS. You take dark runs, you want to save pedestals. So this will be the first of the three things. So the first thing we're going to do, it's just like the Wizard of Oz, except here you're going to follow the green squares instead of the yellow brick road, and we don't have a catchy song for it. So you're going to click on the first green square, and you're going to select your hutch, which in this case is going to be XPP. Next, you're going to select your experiment, because that's turned green. There's a lot of experiments in LCLS that change every week. It's one of the most difficult problems we have, the rate of change. Turns out we're lucky because our experiment's the last one in the list, XPP 215. So we don't have to find it in the big one. It's easier to find in the big list. And click on that. We've got our hutch, we've got our experiment. Last thing we're going to select is our detector. This is the list of area detectors. They're supported by Caliban, actually one waveform detector. We're going to select the CS pad detector because it's one of the more complex ones. Okay, so now we've taken a dark run and we want to deploy constants for that. One of the big things I think that PS ANA helps with is it manages your run-dependent constants. So you're running for 3 days and things change over time. And main thing that people typically deal with is like the dark images. But other things that can be run dependent, your geometry can be run dependent. On this day, these things were positioned this way. On this day, they were positioned another way. We can do that in a run dependent way. We can deploy masks that are run dependent. Say one day you wanted to mask out this area of the detector. For other runs, you want to mask out this area of the detector. So this tool manages all that run dependent stuff in a fairly seamless way. So the thing we're going to do right now, actually let's do the mask first. So we're going to click on the ROI tab. This is what's going to let you draw on your detector image to make a mask. Everything's going to be a NumPy array in the end, so that everything will come down to, when you get back to your Python, it's just going to be a few lines. So the first thing we have to do is we have to select the geometry file, which is how your unassembled image is going to turn into an assembled image. So that's step number 1 on the menu on the ROI tab. And now to see the geometry file, you're going to have to click on Annotate, and then click on your directory. For me, it's CPO, but you should click on your directory name, or if you're somewhere else, you're in your own account. Again, you have to click on Annotate, and get back to the directory that we were working. And now we select the file that we saved with that previous script. Called ND-array.txt. So that's our picture. Now step number 3, you just click on it and it's going to glue together the 2 pieces from steps number 1 and 2, the geometry plus the unassembled image, to give you an image that you can draw on. So we just have to click on number 3 and you're done. Number 4 is Open Mask Editor, which looks like this. This is where you're going to draw. Now, you don't see much to draw on here at the moment. And this is where the left and right click come in. And if you can't do this, don't worry about it. It's not a disaster. Okay, so the way these menus work, and this is all Mikhail's work. You left click to set the left boundary, and you right click to set the right boundary to kind of zoom in. This is an intensity histogram of all the pixels in the image. We just can't see them yet. They're there. So we have to kind of zoom in on the color scale. You can see the color scale down here at the bottom. And so there's our CSPad image. Normally we would see rings here or something like that you would generate if you generated a powder pattern. Right? We have some code to do this. We actually would like to make it publicly available, but we haven't. Okay, so we're going to start drawing. So right now, you can see over here on the left, we're in zoom mode. And zoom mode means that you can kind of click and drag to zoom into an area. So now we're going to start drawing. So we're going to click on Add, right below zoom. The add will turn green. And what we're going to add is a circle. Click on the circle. You can see there's a number of shapes. And we're going to draw the circle. And I'm intentionally covering some of the gaps so that you're going to see how this works. And now we're going to add a rectangle. Come back here, click on rectangle. And again, click and drag to draw your rectangle. Okay, we're going to save our mask. save mask. It's kind of part way down towards the bottom here. Okay, I think it's okay here to use the default file name. So you can click on save. And what that's doing is it's saving it back in the unassembled, a few different ways, in the unassembled form, so that you can use it in NumPy. You'll be able to read this mask in. There's a bunch of different masks that you can ask for, in addition to, so this is the mask that you draw, but you can get other masks. This gives you the mask of bad pixels that were found. If you set status equal true. And this is in that detector interface. So you ask the detector, give me a mask, and get a list of bad pixels. This is run dependent. You can get the edge pixels, because often people want to discard the edge pixels in these complex detectors. There's a funky thing in the CS pad detectors. There's big pixels in the center of a 2x1, so you can get those big pixels. There's unbonded pixels. You'll see them in a picture that comes out of this. And you can get also the neighbors of unbonded pixels too. And the idea is that when you call this, you can specify which masks you want, and it will kind of OR them together, so that you'll get a combination of whatever these mask pieces are that you want. So you can specify one or many. We do have a tool similar to what Christopher has. We call it HDFC for doing alignment. So if you click on the Geometry tab of CalibMan, and then we would select an input geometry file, step number 1, clicking on the left. And then step number 2, we again select this ND array that we've saved, which ideally would have some rings on it or some features that we could use. Middle click. This is not ideal. It turns out on Mac, we looked at this the other day, to get middle click on Mac, you have to install third party. We have this idea of hierarchy of the geometry, where CS pad, and this pattern is going to be true for detectors in the future of LCLS. It's true. This is PNCCDs, EPIX detectors, CS pad detectors. They're all these complex detectors with different levels of geometry. So we select, I'm just going to know it's this one, and then select quad number 3. And set it to move by 1,000 microns to this window right here. And then if you click plus and minus, you can see that big square move around. We're trying to as best we can with the manpower we have, actively support the experiment geometries. And it can be tough, even getting rotations of different detectors relative to each other. Correct can be difficult. Oh, I forgot to say, we can save this geometry with the save button down here. And then that could be deployed in a run-dependent way. And these geometries get picked up automatically. Get the right one for your run number if you're moving things around. The det.image call, a simple one line that will take care of picking up the right geometry. So you can remain this. And then we're going to show runs all. And you should see run 54 and run 59. And you can mark, too much detail, you can mark runs as being dark in the logbook, in which case you can select only dark runs to be shown, and it won't show you all the runs, it'll just show you the dark ones. So you don't have to go through a big list where you can list runs in a certain range. So for run 54, we click on go. And this is going to submit a batch job, which is going to go and analyze 1,000 events. And the fact that if a bunch of us are doing this, it might take a little bit. Normally the turnaround time on this is about 90 seconds, I would say. And this is going to do everything for you. It'll calculate pedestals, it'll calculate bad pixels, it'll calculate noise values for each pixel.
It's slightly small question. What about gain correction?
So gain corrections, there are two for CS, it's detector specific. We're doing more of per pixel, a little bit more of the per pixel gain corrections. Which means if we have flat field data, we have tools now that are generic. Now you might want to look at it before you deploy it. So you can plot an unassembled image. So it's just the array, so there's no geometry here. But you can see most pixels have noise around 5. Some of them are a little lighter blue, which means that they're out here. So you can look at noise values, you can look at 3 things.
What is 5? What are the numbers?
These are ADUs. So 5 ADUs would be the noise level for this particular. And then the last thing, which we won't do because we don't have permissions, is after you're happy with the calibration, you can click deploy, and you can specify the range of validity for this, and we manage all the ranges for you. So mostly you can just click deploy and it works. A lot of times going through the GUI is pain, because you keep doing it over and over, you get tired of clicking. There's a command line interface that does the same thing. And Kyle wrote a little script, which gets used quite a bit. It's a one-line command, you just change the run number, and it will do all of it for you. So that's everything we're going to do with Caliban. Then you can set your peak selection parameters. Minimum number of pixels, maximum number of pixels. Kyle might have to, can you remind me what these 3 arguments are, Kyle? This peak finder will work for all detectors. EPIX, PNCCD, Opal, will work for all of them. Around the peak that you're going to use to evaluate the local noise so that you can cut and signal over noise. And it's going to run over 2 events and print out a list of peaks that it finds in those 2 events, where they are, the number of pixels, and their total amplitude. This is the stuff that we would like to put somewhere so that you could call the same Python routines whatever lab you're at. And the thing that we're trying to do right now, there's a group at BNL that's started up this project called Scikit X-ray. If any of you are familiar with SciPy for Python, SciPy for Python is scientific algorithms, and it's installed everywhere in the world where you use Python for scientific stuff. And there's this idea of Scikit, which is like a specialized SciPy for particular fields. There's a Scikit for machine learning, for example, that David just installed last week into PSA. And there's a Scikit for X-ray science, things like converting distances to cubes and stuff like that, numbers. So that later on you could jump only to the interesting events using the jumping idea that I showed you before, and then ignore all the crap, and you just focus on the ones that are interesting by jumping directly to it. Look at this. And this is an impressive piece of software. At least for viewing images, I don't think it's seen even better. You can like control the colors. There's all sorts of things you can do, like control the so this thing can be updating in real time. We have 1D versions of the same thing. And anyhow, so it's quite nice. And this is an example of this sort. We picked up this piece of software from the web called PyQt Graph, and it's an example of, I think, what we should move towards, getting all the reusable building blocks, including for X-ray science, out there in the cloud so that they can be reused by lots of people. And getting the fast feedback that you need to be able to make decisions. You can run the analysis now with this new feature in batch. as soon as the run starts. And hopefully your analysis will finish very quickly after the run ends. If you're willing to tolerate a little more complexity, you can run from shared memory, which lots of experiments have done. And we believe this is a model we think is right around the world, and we're actively talking to other labs. And they are supporting Python, thinking about scikit X-ray. And we'll see how it develops. The documentation, which we've tried to make somewhat more concise. It's not perfect, but